Hello, everyone, and welcome to vLLM Office Hours number 19. I'm Sasha Zelanovic, and I'm a Principal Product Marketing Manager here at Red Hat. Big fan of vLLM, of course. I'm also joined here by Michael Going, who is the engineering lead at, well, it says Neural Magic, but also Red Hat. He's the principal engineer software engineer at Red Hat, and also a vLLM committer. And then we're pumped to welcome Roger Wang back for the second time. So Roger is a senior machine learning engineer at the ML platforms team at Roblox. He's also a vLLM committer. Roger spoke to us during these office hours back in August of 2024 about, multimodal LLMs in V0. So now we've learned a lot, and we're here to tell you more about a same topic, but in vLLM V1. So welcome, Roger. And I know your team at Roblox is watching you here, so I want to say hi to all of them too. So Michael, can you please go to the next slide?
Of course.
Just a couple of housekeeping items, guys, per usual. So if you want to interact during these office hours, we are always welcoming that. You can turn your camera on if you're in a position to do so. We'll have a dedicated Q&A at the end, like we usually do. But if you have something to say, you can just start talking. You can also use Zoom chat to ask questions at any time, and we'll, get to those questions as they come in. So let's do our little fun thing that we do every session. And hi Robert, if you just want to pull up Zoom chat right now, let's test it out by telling us where you're dialing from. So pull it up and tell us the country or city or state where you're dialing from, and then hopefully we'll get a new flag that we can add to the list of running flags in the bottom right corner here. Lisbon PT, that's Portugal, right? Is it Lisbon, Portugal?
Yeah. I love Lisbon.
I love Lisbon too. I was there actually 2 Septembers ago. Time flies. Israel, beautiful. I think Portugal I don't see a Portuguese flag here yet. So great. I love adding new flags. That's awesome. Texas, North Carolina, Virginia, Boston. Hello, Michael from Boston, Massachusetts. San Mateo, California, of course, New Hampshire, Texas, California, a lot of US, of course, Portugal. Nice. Hi, Luis, welcome. Pumped to have you. Brazil always represented. That's awesome. Thank you, guys. So thanks everybody for coming from all over the globe. It's awesome to see how diverse this community is and how everybody is eager to join no matter where you are. So so we are recording this session. Actually, I should push a live right now. We're also going live. I apologize about that. So give me 1 second. So we are recording this session. We will edit the recording and share it with all of you via email. Most likely early next week, either Monday or Tuesday. You can also find that on our Neural Magic social channels as well. And Adi is about to put the live links to LinkedIn, Twitter, or X, and YouTube in the chat right here. If you want to help us spread the word about this event, feel free to do so. Michael, can you go to the next slide, please?
Yep.
So we've been asking the team here or the community here about topics that we should cover in the future office hours. Thank you so much for overwhelming response. Honestly, it's so good to see what people are interested in. You can always do that. We don't have to run official surveys like we did in the past. If you want to see something from these office hours, come to the vLLM Slack, to the office hours channels, and let us know, or reach out to any of us here on this call. You can also use the Zoom chat or speak up and let us know what you want to hear from us. So we heard that we want to the community wanted to learn about multimodal inference performance. So here we are today. That's amazing. We'll be sharing the vLLM V1 update and also be talking about the vLLM production stack in the next 2 office hour sessions. We'll share those on the next slide. One that's always top of mind for everyone seems to be metrics and observability. And we are working internally to also make that session happen. So just stay on the lookout for that. You can go on, Michael. So there is a lot to cover here. So I'm going to do this very quickly, and I'm going to pass it over to Michael and Roger. So there has been 2 releases already that Michael is going to cover. So V0.7.0 and 0.7.1. I was actually told that 0.7.2 just went out a few minutes ago. So we'll definitely cover that in the upcoming office hours. But Michael will talk about Torch compile support. He'll cover V1 alpha and obviously DeepSeek V3 and R1 optimizations in vLLM. So I don't want to steal Michael's thunder. He'll do that in the following slides. So again, welcome, Roger. We're pumped to hear about multimodal LLMs and all the changes that have been made to make them even more performant in V1. So we'll pass it then to you. And as I mentioned, upcoming office hours, link is here. I believe Michael shared the deck. You can click through all of these links. In 2 weeks, we'll explore V1 Alpha. Our Robert Shaw, who is a vLLM committer and director of engineering at Red Hat, will cover this. And then we'll also do the vLLM production stock on March 6th and be on the lookout for more. And one last thing before I pass it over. East Coast, so vLLM meetup, bi-monthly vLLM meetup is coming to the East Coast. We're really excited to have the privilege of hosting this together with Google at the Google offices in Cambridge. It's a beautiful scene. It'll be a fun night of obviously knowledge and activities and networking. It's happening on March 11th, 5 p.m. is the registration. Our doors open all the way through 9 when we'll have networking. We'll provide light refreshments. Anyways, the link is right here. We would love if you are in a position to, if you live in Boston, absolutely, Madhu. So I'll put in a second. If you're in Boston or can make it to Boston on March 11th, please register. We will have capacity. It is 150 people, so we just opened it. There's plenty of room right now, but if you're thinking of coming, please do join us. Anyway, so Michael, I'm going to pass it over to you. I believe it's your turn.
Yeah, thanks so much, Sasha. That was action-packed start, and we'll continue it on. So as an introduction, as always, if you aren't familiar with vLLM, it's the standard in open source model serving for LM inference. It's really fast, easy to use. It works the way you expect it to work with models off Hugging Face. It has support for many dozens and dozens of key models. State-of-the-art inference acceleration research lands in it directly, and not only getting good performance on NVIDIA GPUs like you would expect, but also due to its reliance on PyTorch, it has support for broad hardware backends like AMD GPUs, Google TPUs, AWS accelerators, Intel accelerators, and even CPUs. And of course, it doesn't stop at just text-only models. Of course, we'll be going over multimodal models here today, but also embeddings, reward modeling. vLLM has gotten a lot of use in TRL recently with all this TRPO methods recently from the DeepSeek release. And of course, many inference optimizations like quantization, chunks prefill, prefix caching, application level features like tool and function calling, structured outputs, and parallelism, so you can distribute your models across multiple devices within a node, and then multiple nodes, especially as you want to run large models like DeepSeek. So a bit about Neural Magic and Red Hat and what we do there. We're a top commercial contributor to the project. I'm a committer, as is Roger from Roblox. We work on all sorts of things, particularly quantization, performance in general. We've worked a lot to bring, along with Kai Chao also leading on Torch Compile and starting to add custom fusion passes as we hope to bring sort of graph compilation to Python and PyTorch. We've worked a lot on the system overhead, particularly a lot of this work in V1 and reducing or simplifying the scheduler and reducing CPU overhead has been critical for making sure we get good performance under high QPS loads. And then, of course, production features for our customers and for the community to get better metrics and dashboards outside of vLLM so you can understand your serving metrics and make sure you're meeting your SLOs. We also work on LLM compressor and compressed tensors under the project and expanding the amount of quantization and sparsity that's available to users in the community and trying to reduce bifurcation with all the different checkpoint formats. So yeah, that's a spiel on us. We have quite a few blogs to call out that we think you should check out since the last office hours. There was a great announcement in vLLM being an inference provider in the Llama stack led by Meta. This is great sort of community adoption. We at Neural Magic, our research team, recently released some evals detailing how models, particularly Llama models, 8B and 70B, at different levels of quantization, handle under long context tasks. So trying to expand our evaluation metrics and share them openly with you so you can make better informed decisions about what level of quantization is appropriate for your accuracy preservation levels. Um, of course, as I'll cover shortly here, we have a blog covering the improvements that have landed recently for DeepSeek models that have really allowed us to push throughput much, much higher and make VLM competitive and state of the art here in open source. And of course, we have a nice blog on VLM v1 and an overview of sort of a lot of the new things there that will be going into detail over the following weeks in follow-up blogs like Torch Compile. So yeah, now getting to the specific releases, a lot to cover here, but in 0.7.0, this is sort of where we say, VLM v1 alpha is ready to be tested. You can, of course, we're not waiting until a v1 release, but the v1 backend has been available for a while, and you can access it through just setting the environment variable, VLM use v1 equals 1. And this will allow you to start using it. There's still a good bit of things that aren't supported, like log probs and structured output that we're working on getting straightened out right away. But it should certainly work for common workloads and common models, and we'll be expanding support as we go along. So definitely give it a try and let us know if anything breaks. We want to fix that. We've also been adding a lot of methods for post-training frameworks and RLHF libraries VLM has been integrated into. So you can modify the model weights in VLM while it's loaded and hosting the model, or put the model weights to sleep, take them off the GPU memory, and reload them back on later. Just so you can have more flexibility when you're trying to use VLM in a larger post-training process. As I mentioned before, Torch Compile is a first-class citizen, and you can also try that it's enabled by default in v1, and you can try it manually with the -03 parameter. And we want to call out, this release was a long time coming, and we had over 400 commits from 132 contributors, which is just really amazing. We actually went over 800 contributors in VLM just over the past few weeks. So yeah, really thankful for the community. A lot of new models have been added. And I won't cover them specifically, but particularly for vision language models, a key refactor being the merged multimodal processors have been starting to be implemented and backported to models. So particularly if there's a model that you're interested in that hasn't implemented this, take a look at the guide and see if you could be interested in contributing this. And this will make it really much easier to get all these various models supported in the new v1 architecture. Other key things is, we now have native support on Apple Silicon, so you can build VLM from source on your MacBook without needing to be in a Docker container. There's also a good bit of optimizations for AMD TPUs. We're trying to expand out the support of features in x86 hardware. And a really key thing is more progress on the out-of-tree hardware support as we have sort of key new hardware backends from the Ascend hardware and the Tenstorrent hardware, as well as the IBM Spire hardware currently using those pathways. As for other things, a key thing was we landed Flash Attention 3. This doesn't include the FP8 attention yet, but this offers really, really sort of large improvements on particularly H100s and Hopper GPUs. And this is particularly useful for V1, as V1 sort of always runs with chunk prefill. So we're always mixing prefills and decodes. And Flash Attention 3 has particular optimizations that make this really reduce the overhead of that abstraction. And another key thing for people that are interested in re-rank APIs, you could sort of hack this together using the Scores API we already had in the OpenAI server, but now we have explicitly Gina and Cohere compatible re-rank APIs. So if you're familiar with those hosted services, now you can host them yourself with vLLM. Now, to also cover the other release that came out, vLLM 0.7.1. This was a key release where we focused on DeepSeek optimizations for V3 and R1, also V2 technically. And the majority of the improvements here were optimizations for the MLA kernels, or for really implementing MLA properly, which gives a lot of compression benefits that I'll shortly cover. And tuning the FP8 kernels, FP8 blockwise kernels that are new with the DeepSeek V3 model that we currently just had implemented in Triton, which we added some tuning for. But now we also have custom Cutlass kernels that are much more optimized, and I'll show some of those results afterwards. Yeah, and then other things in this release are with respect to the V1 architecture. We have some design documents that are starting to be filled out here. Really, a key one on how zero overhead prefix caching was achieved, which is, I think, worth a read, because now we enable prefix caching automatically and by default in V1, whereas it had to be an opt-in thing in V0 before. And we've also been working particularly on bringing metrics and logging, so you can start hosting your Prometheus dashboards again on the V1 engine, and that should hopefully be a seamless transition over the next few releases. Yeah, I think most of the other things sort of stand out for themselves, so we'll leave it at that. And then just to quickly cover sort of what MLA is and why it's useful. So you're probably familiar with multi-head attention or grouped query attention. These are common for llama models. But a key thing that DeepSeek proposed in the DeepSeek V2 paper was multi-head latent attention, otherwise known as MLA. And this is sort of an extreme form of KV cache compression by that's still very accurate, as it's kind of an accuracy equivalent to multi-head attention, but you have this separate process where when you store the KV cache, you compress it down to this latent KV space, and this gives you sort of massive KV cache compression improvements. And here on the right, we have some comparisons for DeepSeek V3 on different hardware configurations, where between using our original sort of emulated multi-head attention versus the new MLA, we're able to see basically a 10x improvement in the maximum amount of tokens that we can host with the model. This is really important for batching. And so for the workload we were benchmarking at, for 1,000 tokens in, 3,000 tokens out, which we think is pretty representative of reasoning workloads, allows us to really increase the batch size to a much more good hardware utilization number, over 100. And then the other thing is sort of the Cutlass FP8 blockwise quantization. Unfortunately, don't have that good of a visualization here, but the key thing about blockwise quantization is we're not just moving along one dimension like channel-wise or group-wise quantization. We're now considering two-dimensional blocks of your weights or your activations and trying to assign and find the best scale for quantizing those blocks. In the case of DeepSeek V3, they're 128 by 128 blocks. So this means for every 128 by 128, weights, we have one scale chosen to best quantize those. And this can be much more accurate than just pure channel-wise scales, where maybe the dimension you don't have the scale, the row-wise dimension you're on doesn't have any sort of grouping to help get more fine-grained quantization here. And on the right, we sort of have a benchmark graph of where our Triton FP8 blockwise kernels were before for various matrix multiplication sizes. And with our new Cutlass FP8 blockwise kernels, we're able to cut down on the latency for them greatly and reduce the overhead of the linear layers. So really, we can just focus on the attention optimizations, which are the more complex part. So without further ado, I would like to hand it off to Roger to talk about multimodal in V1.
Thank you, Michael. Can I share my screen?
Yeah, go ahead.
Roger, I know I introed you in the beginning, but you should do another set of intro just for everybody to join after.
Can you see my screen? Okay.
Yep.
Hi everyone, Roger. Today I'll be talking about the enhanced support for multimodal models in VR and V1. And first of all, just to let me introduce myself, I'm a software engineer on the ML platform team at Roblox, and we are actively hiring. So please take a look at this link afterwards for the job links. And I'm also a VR committer. I've been working on this project for almost a year. I started by making the serving benchmarks to compare different engines with VRM. And later on, I led the support for multimodal models on VIM and here the tracker for this kind of workstream. I also want to call out this team effort. I kind of co-led this work stream with Cyrus, and we have a few VIM committers and community members who have contributed like extensively to this work stream. And I see some of you here today in this talk. And also finally, my colleagues at Roblox have been supporting me on working on VIM. So I want to give a shout out to them as well. So, I want to briefly go over like the agenda for today's talk. So we'll first look at like an overview of large language models, what they are, and we'll go through like what went wrong in supporting them in V0, what's changing V1, why we made these changes, how we made these changes, and I'll share the benchmark results to compare V0 and V1, and I'll wrap up with the future work items in this workstream. So first of all, I want to give a like kind of like short intro of what are large multimodal models. So a lot of like sort of state of art LLMs, they leverage a decoder only language backbone with encoder for non-text modalities. And today on VIM, we support text, image, audio, video inputs, and text token out or text output or token output. So when you have an image or audio, you first encode them into embeddings, and you merge these embeddings with the text embeddings, and you send the final embeddings to your decoder-only LLM. So on the right-hand side, we have Lava, who use Clip to encode images into embeddings, merge with text embeddings, and send to a Llama model. And for Quint2 audio, same story. You encode the audio chunk with Whisper audio encoder, and merge that embedding with text embeddings, and send to the Quint decoder-only language model. But that's how overall how these models work. I'll talk about like what went wrong in V0. I won't be spending too much time on like what we had before because you can check it out in my previous talk with also with this office hours. But in VR and V0, a lot of considerations were not made when we added support for multimodality. In particular, it was designed without considering chunk prefill, and it was designed without considering prefix caching, and it doesn't really have a very efficient input processing that I will go through this list one by one. So first of all, what is chunk prefill? Chunk prefill is a feature we added in V0 that allows prompt to be partially prefilled. This means that you can control the batch size and not let your time per output token be too long because it will be blocked by prefill of the full request. So I have an example here. Let's say I have 3 prompts, R1, R2, R3. What chunk prefill allows is that in step 0, we fully prefill R1, we fully prefill R2, but we only prefill the first 2 tokens of R3. In the second step, we kind of continue prefilling the request 3 while decoding for request 1 and 2, and so on and so forth. So this allows us to change to kind of control the latency for each request so that they won't be blocked by long prompt prefilling. The problem with this for multimodal is that chunk prefill assumes like your tokens are discrete and they are causal, and that's why you can do like some kind of like this kind of iterative prefilling. But for multimodal models, these are often like contiguous features that are generated like in one shot, and they can be broken up. You cannot divide images and generate like images one patch by one patch because there's a full attention modules in your vision encoder or audio encoder. And in V0, we kind of assume that requests will always be fully prefilled because back then when we kind of designed the infrastructure for supporting multimodal models, chunk prefill wasn't even a feature on VRN. So we kind of made this assumption that whenever the multimodal embeddings are generated, they can be kind of size merged into a text embeddings directly. But that's not true for chunk prefill because then you will have, let's say, you have 10 embeddings for first image, but your current chunk only have 2 tokens that's placeholders for the image. So you have like a shape mismatch. One solution, one possible solution, we actually tried this a bit, and we could have done this in visual, is that so we track precisely where these multimodal models are, or multimodal embeddings are in the input sequence by looking at their place tokens IDs. And we kind of regenerate these embeddings on the fly whenever needed, and only took part of these embeddings to put into the chunk. But obviously, you can see the issue is that then you kind of have a lot of like repetitive encoder, multimodal encoder execution, because you're just regenerating the same embedding for the same image over and over. This can be a problem for, let's say, this example we have here, like a 64 frame video of this resolution can represent, can have a representation of over 15,000 embeddings in the input sequence. So let's say your chunk prefill size or like batch size is 2,000. This means you're running the encoder, the vision encoder 9 times, kind of repetitively, in order to prefill this whole request. So the way we kind of solve this, it's kind of natural follow-up, is that we don't regenerate these embeddings, but instead we have encoder cache. And the scheduler is also encoder cache or Encoder-Aware when they schedule these requests. On the right hand side, I have a flowchart, but I'll go through them. I'll go through what's going on. So in each step, we still track where the multimodal embeddings are in the input sequence. But the scheduler, based on the encoder and decoder budget, schedule request into the current batch. And in the current batch, since we know where these embeddings are, we can execute the encoder and generate these multimodal embeddings and store them into this encoder cache. This is our own GPU, and I'll talk about why this own GPU. And since we know their positions, when we need to merge them with the text embeddings, they can be retrieved from the cache to be merged with text embeddings and sent to Decoder-Aware. And for prefill, so I guess for chunk prefill, if these embeddings are still needed, then we keep them in the cache. And if the request has been prefilled up with these embeddings, we just evict them otherwise. And I also want to kind of emphasize that right now the cache is designed request by request, meaning if an embedding is no longer needed by the current request, you'll be evicted from the cache to free up space. But this encoder cache can be indeed extended to support caching across requests, meaning if you have 2 requests that share the same image, even though the prompt is different, but they share the same image, the request 2 can share the embedding with request 1 without regenerating the embedding. This is not there yet in vLLM right now, but I want to call that this can be added to vLLM. So question, why is this cache on GPU? Why don't we have this cache on CPU? This is because Torch Tensor to CPU can be very expensive, and sometimes you transfer these big embeddings from GPU to CPU. That alone takes more time than the encoder execution itself, not to mention to get them back from the CPU memory. And some other people might ask, why not? You might realize from this kind of a step, we're running encoder and decoder sequentially. Why don't we run them on different CUDA streams? One reason is that then you have to kind of store the embeddings back again to CPU memory. There might be some workaround for different CUDA streams to share the same share memory, but also another reason is that this will require very careful pipelining of your encoder and decoder. You definitely don't want your encoder to eat too much flops for your decoder. We did some little mini benchmarks and realized this kind of complexity is not worth the performance. Sometimes it also depends on how big your encoder is. For example, in Lava, the encoder is 400 million parameters, but for IntenVL, it can be up to 6 billion. So encoder can be very expensive sometimes. I also want to emphasize that it seems a simple architecture design, but the major change we did was we need to rewrite all the interfaces for multimodal models, because previously we don't schedule embeddings image by image or audio by audio. We just grab whatever in the input request, because we always assume they can be pretty prefilled, and we flatten them and merging into text embeddings. But now that we need to schedule them in a fine-grained manner, So embedding is need to be stored by their like corresponding to their data items in the encoder cache in order for the scheduler to grab them from the cache. A lot of work has been put into like making sure the new all the models we have on vLLM can be, I guess, multimodal models we have on vLLM can be compatible with the new kind of architecture design. So next, I want to talk about prefix caching. So in V0, prefix caching is exclusively based on caching the tuples of token IDs. And this is a problem because for multimodal models, their kind of like embedding representation in the original input prompt is always placeholder token. And this placeholder token and their token ID are always the same across all requests. So for Lava, it's always just one little image string, and 32,000 is the token ID for the string in the input prompt. And as you can see, you will have a correction issue if you only hash based on token ID. So if say you have two requests with the same identical prompts, very often that's like what evaluation does. But with different images, then you will have a correctness issue because solely based on token IDs will like have incorrect prefix caching for these two requests. The second request will think it had already been cached, but the image is different. And this is the reason why we have to turn off prefix caching for multimodal models, kind of in a forced fashion in V0, even though some people might just use it for text-only inference, which is pretty sad. So in V1, what we did is that we add additional kind of metadata to be considered for prefix caching. I won't go through too much details here, but TLDR is that now we can use hashes of multimodal data. So hashes of images, hashes of audio chunks to be part of the hash of the block. And I strongly encourage you to check out this design doc Cody wrote out for V1 prefix caching with multimodal data and also other improvements. But I'll just like briefly explain the high level idea is that now we can consider additional metadata for prefix caching, and that just works out for multimodal models. And finally, I'm going to talk about multimodal data processing. And this is in fact the biggest performance boost we get from V0. One of the biggest performance boosts we get from V0. So in V0, the interface, the front end takes a pillow image, and these pillow images has to be converted to tensors to be consumed by the vision encoder, or audio wave file have to be converted to tensors to be consumed by whisper encoder, etc. But this is a blocking CPU operation in V0, and this means the GPU kernels will always be blocked by the kind of overhead from CPU. Initially, we thought it wasn't a big issue because for the models like Lava, their kind of processing operations is very simple. It's simply like a resize, and that was it. But as more and more models come out with more like complicated pre-processing, we realize this is a big issue, and the performance hit is especially bad for offline batch inference because people are sending like a list of 1,000 prompts, and very often you see like the GPU getting blocked by CPU operations. We have to admit that this was like a design oversight. We shouldn't have designed this way. So in V1, we optimized the engine loop. You might have seen this chart from other talks. So in V1, we have two processes behind the API server and the interface of LLM. Process 0 is responsible for anything that's happening on CPU, and process 1 try to keep the GPU running hot. So now we have the input processing that converts pillow to tensors happening in process 0, and the forward pass, the GPU work happening on process 1, and they are not blocking each other. So here's a comparison of how the pipeline looks like. In V0, we will always have GPU kernel forward pass getting blocked by input processing. But now in V1, they are kind of running on parallel as long as the forward pass has already received the input it needs from the previous step. I guess the process 0. The other thing I want to talk about that we optimize for multimodal kind of feature generation is feature caching. So typically, when you serve a vLLM inference server, or when you run vLLM offline batch inference, the CPU memory is actually not that much used. since most of the work is happening on GPU. So we decided to add a cache for converting the raw data to tensors. You can think of it as I know I have to run my image through this processor to generate tensors. Why don't we cache it since we have so much CPU memory? And the way we design it is that we have two caches, LLA cache in both processes. I will go through the steps here. So first of all, we want to utilize the CPU memory to cache the generated features from the raw data format. And we can use the same hash for prefix caching that I talked about before. We have two mirror caches, meaning that if the cache in process 0 has seen the same image before, then the only thing it needs to send to process 1 is the hash itself, because the two caches are mirrored. Otherwise, it will send the hash along with the features that's generated to be cached in the process 1 cache. We designed this way so that there's less data transfer between the two processes. And sometimes the data transfer can be very huge. They can be like a very big tensor. So we designed the mirror caches to kind of optimize this data transfer. And I also call out that with this, you can think of it like a multimodal prefix. Like, let's say you have a multi-turn image QA. It's the same as prefix, like text-only prefix caching, because now the features are also cached. So the generation from image to tensors is also kind of skipped throughout this process. And this is a big improvement when it comes to like utilizing prefix caching with multimodal models. And that kind of wraps up with the kind of changes we did for view 1. And I want to just give a shout out to the whole team. This very, very much a team effort. And I'm not the only person responsible for this redesign. And I think a lot of the things on view 1 are co-designed with each other. For example, prefix caching, we kind of redesign it to be able to work with multimodal data from the get-go. Same with engine loops, same with feature caching. And I also give some bonus shout outs here. So Cyrus and the Isotropy has been working on the merged multimodal input processor. This is not particularly related to view 1, but like benefit overall vLLM as well. And also Michael on this call has been working on adding multimodality support on TPU. Okay, let's jump to benchmarks. And I think that's what most people are here for. So benchmarks, we have two sets of benchmarks. The first is online serving. The second is offline inference. So for online serving, we have Quint2VL 7B running on Vision Arena dataset. So Vision Arena dataset is a kind of a Vision QA dataset from Skylab. Each request is different because they are sampled from real world traffic. So with different prompt and different images and different output. And on the x-axis, we have the QPS here. And on the y-axis, we have the mean latency for the overall the traffic. As you can see here, in low QPS region, the difference is not that huge. But when we scale up the QPS, we can definitely see the difference between throughput between V0 and V1. We also compare V1 to another open source alternative, and we observe that in V1 we are still performing the best in a very high throughput regime. Second, we have offline inference. This is really to show kind of the benefit of like caching design in V1 vLLM. So for this benchmark, I'm using the MMU Pro Vision dataset. That's very often being used for eval these big models, and we're running Momo 72B on TP4. And on the y-axis, this is the offline throughput relative performance, and we use vLLM V0 as a baseline. So comparing vLLM V0 and vLLM V1 with no caching, we already have like a 40%-ish performance boost. And you may observe that you have 3 lines here: 0% repeat, 50% repeat, and 100% repeat. This means like how many of the requests in your dataset has been repeated to measure we're trying to simulate the benefit of prefix caching. So when we turn on both caching, which is actually on by default when you use vLLM V1 now, for 0% repeat, which means every prompt, every request has different images, different prompt, there's a little bit performance hit, but very minimum. You can kind of like expect that because we're doing additional caching and hashing of the input prompt and the images. But when you have when you request share some prefixes and share to maximum like 100%, well, we can see the performance boost is very significant. I want to emphasize that this is not just prefix caching, but also benefits a lot from feature caching, because now that CPU operation that generates tensors from images are also skipped, as well as the KV cache generation as well. So that was the kind of benchmark I want to show for the two scenarios: offline serving, offline inference, and the online serving. And I want to wrap up with some future work for this workstream. So first of all, definitely want to wrap up V1. Not all multimodal models are supported by V1 yet. So feel free to check out this like V1 column in the support list of models. If it has a green check mark, that means it's supported. Second is we want to also optimize the mixed modality inference. It's actually not very common these days, but we also kind of expect it coming up this year, where people are sending both audio chunk and the image and the text input together for inference. Today, most use cases that we've been seeing is image plus text, audio plus text, video plus text, but not too many people are messing with mixed modality inference with prompt or with text. But we do expect this to be a kind of like popular use case coming up this year with more with better like capabilities from the models. And in order to kind of support that, we also need to make the API server itself more robust when it comes to like processing these input data. Can be like MP4 file or like audio wave file or big images payload. And people have been asking a lot about, are we going to support multimodal output on VLN? Does it make sense to support multimodal output in VLN? And first of all, no diffusion. We have discussed that a few times. That's not what we're gonna do on VLN. But we do want to support autoregressive multimodal generation that's backed by like a decoder-only language model. So there are actually a few examples, right? So first of all, mini CPMO that Michael talked about previously, they have like an audio output capability using the Whisper decoder, but we're not using that. Actually, not Whisper decoder, but we don't have that support yet. NVIDIA Cosmos that takes video input and output a video, and the backbone is also like a decoder-only transformers. And finally, as you may know, DeepSeek Genus Pro, also leveraging a decoder-only language model, but it discretely like tokenize images so that you can also detokenize images from tokens to generate images. So this kind of like models we do want to support, and it is on our roadmap indeed. And finally, multimodal input streaming. So there are some use cases coming up that stream videos into the API server and generates, I guess, doing the prefill on the fly when the video frames are getting streamed in. Today we don't support that. Today we just take a video file or like an audio chunk and do the processing. But we don't have a mechanism for us to kind of pause prefill and wait for the wait for the multimodal data to be streamed in. So this is something we want to look into as well, as the kind of a real-time interface become more popular for these models. And that was it. That's everything I want to talk about. And thank you all for listening. You want to take it away?
Thanks a lot, Roger. That was wonderful.
Thank you. I'll just bring and switch back.
Okay, sure.
We can open it up for questions. I can start. Roger, I have a two-part question for you. Part one should be easy. So my 6-year-old knows all about Roblox, but there might be some people here who are not too familiar with Roblox. So if you can give us a 30-second intro into just what Roblox is as a platform. And then part two, and I'm really interested about this one, is, and if you're comfortable sharing totally, how is the Roblox using vLLM and multimodal LLMs in production? And if you can tell us, how you guys are using it, something that we can take back with us.
I can definitely answer the first one. So this one, Roblox, there's a common misconception that we make games, but we actually don't make games. We provide a platform for developers making their games, and for others to come to the platform and play the games and interact with each other, make friends. So Roblox is more like a social platform in the content, in the format of games. That's Roblox. For multimodal models usage at Roblox. So one example I can give you is at Roblox, we care very much about safety. Safety is one of our top priorities of the company because majority of the users at Roblox are kids, right? So one use case we have at Roblox is to use multimodal models to do image moderation. And sometimes people can upload asset. By asset, I mean like a 3D mesh in the game, and these assets can be like dangerous for kids to see. So one way to moderate these 3D asset is to take screenshots of these asset meshes and send them to like a multimodal model to do a kind of like a image understanding based on some like prompt engineering policies, right? So for example, I can take a screenshot of a gun, and my policy is my asset cannot have a gun. So if you send that to a vision language model and ask it, is this image violating the policy? Most cases, the model will understand that it will recognize the image is gone and the policy says no gun. So that was one use case. Some other use cases that I came across with is that you take screenshots of a game and you send that screenshot together to a multimodal model to kind of generate an understanding of the game. So when new games comes up, sometimes we want to have a quick understanding of what's inside the game, what's fun part of it. So using multimodal models to understand these games, like content understanding, is also like one exciting use case.
Yeah, really cool. Glad you could share some there. I actually have a question on the sort of real time input streaming. I actually don't even know how this works with modern architectures. Like it's kind of like I can understand for like Whisper, like that's a classic model here. Like it's kind of, you have to split your input audio into like chunks of maybe like 10 seconds or 30 seconds, and you like gradually work on that and maybe can queue up like future chunks. But with with maybe not like a cross encoder model.
The way I think of it is that, let's say you have someone is taking a video, right, from their iPad, and the frames of the video is taking like real time, right? Because they're taking it like on the fly, like they're taking it like in the real time. One way to kind of like understand the video content is you only start prefilling them once they pause it or like once they stop it, and you send the whole video chunk with some prompt that you have to the model to understand, right? The other way you can do it is that when the videos are being taken, the frames and the prompt can be sent to the LM on the fly, like at the same time. And the batch will have I guess the scheduler will need to have a way to kind of pause prefill for this current request, telling the scheduler, hey, this request hasn't been done prefilling, even though there's no data coming in yet. There need to be a signal for the scheduler to tell, I guess, the batch that now you have more data. Let's put it in there and do prefill, and let's put it in there and do prefill. It's more like a chunk prefill kind of a nature, but except your new data is coming in on the fly versus waiting in the queue. Does that make sense, Michael?
Yeah, so it really will be, for models like this, interspersed with the decoded tokens. So it's just like now we will like schedule some new tokens to be pre-filled after we've pre-filled and decoded for a while, and now we want to pre-fill again and then decode again. Yeah.
Kind of the idea, yeah.
Okay, cool.
I guess another thing is like maybe sometimes you don't even want the scheduler to think the request has finished pre-filling, because there are more frames coming in before we go to decode. So like you are pausing some request you're getting requests from the queue to the batch, pre-fill some and put it back in the queue because there are more data coming in the real time. This is a bit complicated though.
Yeah. I see.
So this is Val from WECA. I've got a kind of an open-ended question, Roger. Really fascinating presentation, and I'd love to see more and more multimodal models coming online here. We're working on Mooncake and some extensions to obviously disaggregated prefill and decode, where there's no more limits to the amount of KV cache. And with some asynchronous I/O optimizations and using GPU direct and low latency microsecond level storage, what are some of the use cases you see around not just prefix, but especially feature caching, when now you can have effectively terabytes and petabytes of KV cache at microsecond latencies? And with async I/O, it can be faster than some DRAM, VRAM to DRAM transfers.
Yeah, I think feature caching is always an interesting topic. Because back in V0, we kind of try to let the users themselves to do the caching themselves. Right? So one thing we are kind of enabling in V0, since we realize it's kind of a overhead issue, is that we open up an interface to allow users to input image embeddings or like video embeddings directly to the model. So you don't actually run your processor or your encoder at all. You just send me the embedding. I'll put it back in the text embedding and send to the decoder model. So I think in V1 we still want to keep that interface open. Actually, in fact, we do have the interface open. And it's kind of like your freedom, right? If you think caching embedding is the right solution for you because you have a lot of spaces on your machines, then you can definitely do that. Otherwise, we still need to kind of serve the users that don't have that much space, right? Or they don't have that powerful compute, and they just want to have a solution that can run end to end. So it's a very challenging problem, like how to make sure both type of users can be happy with the vLLM. And I think right now we are at a really good spot. We still support multimodal embeddings as input, and as well as like end-to-end inference. And I think there's also a lot of stuff that can be optimized for easier way. So for example, if we support multimodal embeddings as the input, one way is that you simply don't load the encoder at all because you don't use it anyways.
Yeah.
We don't have a flag for that. But that's something that's definitely something that can be customized for sure. And on the other end, if I know the only thing I care about is like an end-to-end inference, then the vLLM should be responsible for pipelining, like the stuff I just talked about, like the two processes. Then we should be responsible for making sure the pipeline is done correctly to not have stuff block each other.
Exactly, especially with the infinite context window use cases where we need different kind of attention algorithms. So what Google's done with ring attention, I don't know what we're doing with supporting these kinds of models now that can essentially deal with giving attention to something that is logically already bigger than physical KV cache in HBM.
Yeah, I think there are indeed some work on vLLM that talks about KV cache offload, right? So let's say you have a long context and you have done some prefill for the previous chunks of the context, but now you're running out of space, then you can offload that to KV cache. Offload that KV cache to CPU and continue with your prefilling on your GPU. There's some work around that, and also I know someone's working on more like a more efficient KV cache management for different kind of workload. So today the KV block is designed to work for decoder only models, but I know there has been some work around refactoring this kind of design to support also contiguous features, right? Like image embedding is auto embedding. There are also contiguous features that can't really be broken up that easy. Yeah.
Awesome. Yeah, we'll follow up on Slack.
Thank you.
Nice. Thanks a lot, Bal. Any other questions?
No question.
I have another kind of general question. I think Val's was kind of related to where I was thinking, but are there kind of calls for research you have rough ideas about in this in the space of feature caching or multimodal prefix caching, where it's kind of related to like disaggregated prefill or KV cache offloading. There's like a lot of things to like explore here, and we already kind of have this like hierarchical caching now with like feature caching of that it's like might be good ideas for a PhD student or someone interested to have a starting
Yeah.
point.
Yeah, I think a recent trend, like I've been seeing, is that starting from Lava, Lava always converts one image to 576 tokens, no matter what. It could be a very large 4K image. It'll be resized to that particular fixed size and kind of like convert to tokens. But I think a recent trend we've been seeing is that these representations of images are getting bigger and bigger and bigger and bigger. So Lava was 576. I think the max size for pixel was 4K, and for Qwen2 VL or Qwen 2.5 VL, it's like 8K. So these are getting like these embeddings for images are getting bigger and bigger, and not to mention like some a lot of use cases that are doing multi-image inference, right? You're not just sending one image, you're sending multiple images. So I think an interesting research area is to think about like how to efficiently deal with this kind of scenario where you have like a contiguous embeddings in your prompt that's a very huge and takes a lot of spaces in your KV cache. Maybe there's some work around KV compression, or maybe there's just some work around like how to efficiently I guess it's more about modeling, like how to efficiently extract the features from the images, not just like dividing them into patches and kind of run them through VIT separately. So I think this kind of but there's also like people arguing that this is more like a data problem. As long as you have a lot of data to train your VIT and together with your LM, you have a better understanding of the overall like the overall like image understanding capabilities. I don't know. I think both like arguments are valid, and I think these are still like exciting areas to think about. Even for like image language model itself, we're still like debating between whether we should generate continuous features for images or like discrete tokenize them into tokens, right?
Yeah.
There's still like no it's like there's still no like set architecture for us to do it. That's why I think that kind of area is also very exciting to explore.
Yeah. Yeah. No,
I'm interested for sure too.
yeah. I think I definitely agree. Maybe that's another use for something like multi-head latent attention. Actually, do you know if the DeepSeek 2VL like uses that?
I think it does because I think it does because it uses the V2 as a backbone.
Yeah. Okay. Yeah. As a backbone, but probably the vision encoder is something different.
Yeah. I'm also kind of excited about what's coming out from DeepSeek. My personal take for Genus Pro is that it's more like a ablation study because they only released the 7V model. I think the reason why they didn't release the big model is they didn't have too much like. Hopefully, maybe I'm wrong. I'm just like guessing myself, but I'm like whenever maybe like there's a DeepSeek V3 VR coming up, I'm pretty excited. I'm pretty excited about like how that turns out. And people also have been doing like reasoning on top of these models.
Yeah.
So there's a one exciting work coming out from PKU, I think. It's called R1V. Basically, like they trained, they kind of like post-trained the Qwen2 VR 2B or 3B to have the same capability when it comes to counting as the 72B model. So reasoning on top of like multimodal models is also a very interesting idea to think about.
Yeah. Very cool. Well said. Well, I think we're basically at time here, but if you have any questions, feel free to leave them in the chat afterwards. But we'll clean up here. So yeah, as always, a call to contribute to vLLM. If you love the project and want to help out, you can join in the Slack and ask things, give us feedback, let us know what features you really want. That helps us to decide on priority. Go through the issues queue, look for tags that are interesting to you, and just leave comments on issues and PRs. Just however you want to help out. Of course, we want to call out the next, I believe vLLM meetup. And the first one we'll be doing on the East Coast at the Google offices in Boston, Massachusetts. So register here. We should have the link for the presentation earlier in the chat. Neural Magic, we're hiring. Roblox is hiring. There's a lot of great work to do on vLLM while being, paid well. So have a great time, everyone. Thanks for joining. Thanks for being part of the community.